For centuries, astronomers assumed the night sky should be blazing white. An infinite universe filled with infinite stars ought to flood every corner of darkness with light. And yet, it does not. This puzzle, so simple that a child might ask it, so profound that it eluded the greatest minds for generations, carries within it the shape of the cosmos itself. The answer, when it finally came, would rewrite everything humanity believed about beginnings and endings, about time and the slow expansion of space. If these quiet explorations help ease the mind toward rest, the subscribe button is there for future nights like this one. The question waited nearly 400 years to be resolved, passed from philosopher to physicist, each one circling closer to the truth, and now, the telling of it can unfold. When the sun slips beneath the horizon and the last amber light drains from the western sky, a profound transformation begins. The world grows quiet. Colors fade to gray and then to black. Stars emerge one by one, scattered across an immense dark canvas that stretches from horizon to horizon. This is nightfall, the daily arrival of darkness, and it is perhaps the most universal experience shared by every human being who has ever lived. From the first of our ancestors who walked upright across the African savanna to the billions of people alive today, all have witnessed this gentle transition from day to night. All have stood or sat or lain beneath the darkening sky and watched the light disappear. And for most of human history, across countless generations and civilizations, almost no one thought to ask why. The darkness of the night sky is so familiar, so utterly ordinary, that it seems to require no explanation at all. Of course the sky is dark at night. The sun has gone. What more is there to say? This intuitive response, this comfortable acceptance of darkness as simply the absence of the sun, satisfied humanity for tens of thousands of years. We questioned many things about the heavens. We wondered at the wandering planets and their complex paths. We marveled at eclipses and comets and shooting stars. We built elaborate theories about the nature of celestial spheres and the music they might make as they turned. But the darkness itself, the black velvet backdrop against which all these celestial wonders appeared, remained curiously unexamined. It was simply there, as it had always been, as natural and unremarkable as breathing. Deep within the limestone hills of the Dordogne region in southwestern France, there exists a cave system that holds some of the oldest surviving records of human artistic expression. The Lascaux Caves, sealed by a landslide and preserved in darkness for perhaps 17,000 years, contain hundreds of paintings created by our distant ancestors during the last ice age. By the flickering light of animal fat lamps, these early humans painted magnificent bulls and horses and deer upon the cave walls. They painted abstract symbols and geometric shapes. And they painted patterns of dots that some researchers believe may represent the stars of the night sky, perhaps the Pleiades cluster or the belt of Orion. These ancient artists clearly paid attention to the heavens above them. They watched the stars. They may have told stories about the constellations and used them to mark the passing seasons. But if they ever wondered why darkness filled the spaces between those stars, they left no record of such questioning. The darkness was simply the natural home of the stars, the place where bright points of light could be seen, and that was enough. The civilizations of the ancient Near East developed some of the earliest systematic approaches to studying the heavens. In the cities of Mesopotamia, along the fertile banks of the Tigris and Euphrates rivers, Babylonian astronomers created detailed records of celestial events stretching back thousands of years. Clay tablets from around 1200 BCE and earlier preserve meticulous observations of planetary positions, eclipse cycles, and the rising and setting times of stars throughout the year. These astronomers developed mathematical methods of considerable sophistication. They could predict lunar eclipses with remarkable accuracy. They tracked the complex apparent motions of the planets and assigned profound astrological significance to celestial events. Their astronomical tablets, inscribed in cuneiform script and baked hard for posterity, represent one of humanity's earliest scientific achievements. Yet among all these observations and calculations, among all the careful records of where stars appeared and when they rose and set, there is no indication that anyone asked the seemingly simple question of why darkness existed between them. The dark sky was the stage upon which the celestial drama unfolded, but no one inquired into the nature of the stage itself. A similar pattern appears in the astronomical traditions of ancient Greece, where philosophers and natural scientists proposed bold theories about the structure of the cosmos. Aristotle placed the Earth at the center of a series of crystalline spheres that carried the Moon, the Sun, the planets, and finally the fixed stars in their eternal rotations. Beyond the outermost stellar sphere lay something he called the primum mobile, the first mover, and beyond that perhaps nothing at all, or perhaps the realm of the divine. Ptolemy refined this geocentric model with his ingenious system of epicycles and deferents, producing a mathematical framework that could predict planetary positions with impressive accuracy. Greek astronomers debated whether the universe was finite or infinite, whether space continued forever or came to some kind of boundary or edge. But even these discussions, which touched upon questions of cosmic extent, did not lead to sustained inquiry into why the night sky appeared dark. Darkness at night remained as unremarkable to Greek thinkers as it had been to Babylonian astronomers or to the Ice Age painters of Lascaux. The medieval period in Europe saw the construction of elaborate observatories and the compilation of increasingly precise star catalogues. On the island of Hven in the narrow strait between Denmark and Sweden, the Danish nobleman and astronomer Tycho Brahe established his famous observatory of Uraniborg in 1576. The name meant Castle of Urania, in honor of the muse of astronomy, and the facility represented the cutting edge of pre-telescopic astronomical observation. Tycho designed specialized instruments of unprecedented size and precision. He developed new methods for correcting observational errors and for accounting for atmospheric refraction. Over the course of 2 decades of painstaking work, he and his assistants compiled a catalogue of 777 stars, recording their positions with an accuracy that had never before been achieved. This catalogue would later prove essential to Johannes Kepler's discovery of the laws of planetary motion. Tycho observed a supernova in 1572 and a great comet in 1577, demonstrating that changes could occur in the supposedly unchanging celestial realm beyond the Moon. He revolutionized the practice of astronomy through his insistence on careful, systematic observation. And yet, for all his attention to the night sky, for all the countless hours he spent gazing upward through the slits and apertures of his instruments, there is no record that Tycho Brahe ever paused to wonder why darkness filled the spaces between those 777 stars. The blackness of the night sky was simply the medium through which starlight traveled, the backdrop against which celestial positions could be measured, and nothing more. As you listen to these words, perhaps lying in the comfortable darkness of your own room, your eyes may be adjusting to the dim light. This is a process that happens automatically, without conscious effort, and it takes longer than most people realize. When you first enter a dark space from a brightly lit environment, your vision is quite poor. Shapes are vague and colors are impossible to distinguish. But over the course of 20 to 30 minutes, a remarkable transformation takes place within your eyes. The pupil dilates to allow more light to enter. The cone cells in your retina, which are responsible for color vision and work well in bright light, gradually yield their role to the rod cells, which are far more sensitive but cannot detect color. The rod cells contain a light-sensitive pigment called rhodopsin, and this pigment requires time to regenerate after exposure to bright light. As more rhodopsin becomes available, the rod cells become increasingly responsive to even the faintest glimmers of light. After perhaps half an hour in darkness, your night vision reaches its full capability, and you can see by starlight alone, detecting light that is roughly 1,000,000 times fainter than what is needed for comfortable reading. This adaptation to darkness is something your distant ancestors experienced every single night of their lives, in an era before artificial lighting, when sunset truly meant the end of easy sight. They became intimately familiar with the night sky, with its patterns and rhythms, with the slow wheel of constellations across the seasons. And still they did not think to ask why that sky was dark. The great English mathematician and natural philosopher Isaac Newton published his Principia Mathematica in 1687, setting forth the laws of motion and universal gravitation that would form the foundation of physics for more than 2 centuries. Newton showed that the same force which caused an apple to fall from a tree also held the moon in its orbit around the Earth and the planets in their orbits around the Sun. He unified terrestrial and celestial mechanics in a single elegant mathematical framework. He explained the tides. He calculated the shape of the Earth. He analyzed the trajectories of comets. His achievement was so comprehensive, so revolutionary in its scope, that the philosopher Voltaire would later report that Newton had found the universe a chaos and left it a cosmos. And yet, in all the dense Latin prose of the Principia, in all of Newton's voluminous writings and correspondence, there is no serious treatment of why the night sky appears dark. Newton was aware that the universe might contain an infinite number of stars. He corresponded with the theologian and scholar Richard Bentley about whether the cosmos could be infinite in extent and still stable under the influence of gravity. But the specific question of what an infinite starry universe would look like, of whether it would be filled with light or shrouded in darkness, did not seem to capture his sustained attention. The darkness of night remained, as it had for millennia, simply a given. Consider for a moment just how strange this historical silence is. Here is perhaps the most obvious, most immediate feature of our universe as perceived by human eyes. Every single night, weather permitting, every person on Earth can look up and see the same fundamental fact. The sky is dark. Most of it is black. A few thousand stars are visible, appearing as bright points scattered across this immense darkness, but the darkness itself dominates. It is the rule. The light is the exception. And this has been true for every human being who has ever lived, from the earliest Homo sapiens to walk out of Africa some 200,000 years ago, through every generation that followed, down to the present day. It is a universal human experience, perhaps the most universal of all astronomical observations, requiring no special equipment, no training, no particular geographic location. Simply step outside on a clear night and look up. And yet, for the vast majority of human history, this obvious darkness generated no sustained scientific or philosophical inquiry. The night sky was dark, and that was simply how things were. Part of the explanation for this long silence may lie in the way humans think about absence and presence. We naturally attend to things that are there rather than to things that are not there. A bright star commands attention. A dark patch of sky does not. Light is something positive, something active, something that arrives at our eyes and stimulates our vision. Darkness, by contrast, seems to be merely the absence of light, a privation rather than a thing in its own right. It is difficult to formulate questions about something that appears to be nothing. What is there to explain about emptiness? What theoretical framework could address the lack of illumination? These intuitive barriers may have prevented earlier thinkers from recognizing that the darkness of the night sky was itself a phenomenon requiring explanation, a piece of evidence about the nature of the universe every bit as significant as the light of the stars themselves. And so the darkness endured, unremarked and unquestioned, through the long centuries of human civilization. Empires rose and fell beneath that dark sky. Religions were founded and reformed and transformed. Technologies advanced from stone to bronze to iron to steel. Languages evolved and spread and died. Continents were mapped and remapped. All the while, every night, the sky grew dark, and almost no one thought to ask why. It would take a particular combination of circumstances, a particular way of thinking about infinity and light and the structure of the cosmos, before the darkness of the night sky would finally be recognized as one of the deepest puzzles in all of astronomy. But that recognition, when it came, would change forever how we understand our place in the universe. For now, though, let us simply rest with the darkness itself, the familiar companion of every human night, the backdrop to dreams and contemplation and sleep, as natural and unquestioned as the breath that rises and falls within your chest. In the early years of the 17th century, in a Europe still lit by candles and oil lamps, still governed by the rhythms of sunrise and sunset, there lived a man whose mind reached far beyond the flickering shadows of his study, out past the rooftops of Prague, beyond the spires and the river, upward into the dark vault of the heavens where the stars hung in their ancient silence. His name was Johannes Kepler, and he was born in the year 1571 in the town of Weil-der-Stadt, in what is now southwestern Germany, a small place nestled among hills and vineyards, unremarkable in most respects except that it happened to be the birthplace of a man who would one day ask a question so simple and so profound that it would take humanity 3 more centuries to answer it properly. Kepler came into the world as a sickly child, premature and frail, and his early years were marked by illness and by the instability of a family that struggled with poverty and with the various misfortunes that seemed to follow them like shadows. His father was a mercenary, often absent, eventually disappearing from the family's life altogether, and his mother, Katerina, was a complicated woman, herbalist and healer, who would later in Kepler's life face accusations of witchcraft, a terrifying ordeal that would consume years of his energy and attention. But despite these difficult circumstances, or perhaps in some way because of them, the young Kepler found solace in learning, in the precise and orderly world of mathematics, in the contemplation of celestial bodies that moved through the sky according to laws that seemed, if one could only discern them, to be expressions of a divine harmony. He studied at the University of Tübingen, where he encountered the ideas of Copernicus, the Polish astronomer who had proposed, decades earlier, that the Earth was not the center of all things, that it was instead a planet like others, circling the Sun in the company of Mercury and Venus and Mars and Jupiter and Saturn. This idea took hold in Kepler's imagination with a force that would shape the rest of his life, and he became one of the most devoted advocates of the Copernican system, defending it not merely as a mathematical convenience for calculating planetary positions, but as a true description of how the cosmos was actually arranged, with the Sun at the center and the planets moving around it in paths that Kepler himself would eventually prove to be not circles, as everyone had assumed, but ellipses, elongated curves that stretched and compressed as the planets drew nearer to and farther from the central fire. But before he arrived at those famous laws of planetary motion that bear his name today, Kepler spent years in difficult circumstances, moving from place to place, seeking patronage and employment, facing religious persecution because his particular brand of Lutheran faith did not conform precisely enough to the orthodoxies demanded by the authorities of his time. He was too Protestant for the Catholics, and too unorthodox for the stricter Lutherans, and this theological no-man's land made his life precarious in ways that are difficult for us to fully appreciate today, when such matters no longer determine whether one can hold a teaching position or must flee to another city. In the year 1600, Kepler arrived in Prague, which was then the capital of the Holy Roman Empire and the seat of the Emperor Rudolf II. A peculiar and melancholy ruler who had a deep fascination with art and science and the occult, who collected curiosities from around the world and kept them in his Kunstkammer, his cabinet of wonders, and who employed at his court astrologers and alchemists and astronomers, among them the great Danish observer Tycho Brahe. It was Brahe who had invited Kepler to Prague, hoping to make use of his mathematical abilities, and when Brahe died unexpectedly in 1601, Kepler inherited his position as imperial mathematician, along with Brahe's vast and precious collection of astronomical observations, the most accurate measurements of planetary positions that had ever been made. For the next decade, Kepler worked in Prague, laboring over Brahe's data, struggling to make sense of the orbit of Mars, which stubbornly refused to conform to any combination of circles that Kepler could devise. It was painstaking work, requiring calculations of enormous complexity, done by hand with quill and paper, year after year, until at last Kepler made his breakthrough, realizing that the orbit was not a circle at all but an ellipse, and that the planet moved faster when it was closer to the Sun and slower when it was farther away, and that there was a precise mathematical relationship between the time a planet took to complete its orbit and its distance from the Sun. These discoveries, known now as Kepler's laws, were revolutionary in their implications, but they emerged from a process that was anything but glamorous. A long and often frustrating engagement with numbers and geometry that required immense patience and a willingness to abandon cherished assumptions when the data demanded it. It was during these years in Prague, in the midst of this great labor, that Kepler received extraordinary news from Italy. In the year 1610, the Italian mathematician and natural philosopher Galileo Galilei had turned a new instrument toward the night sky, an instrument that had been invented in the Netherlands just a year or two earlier, a tube with lenses at either end that made distant objects appear larger and nearer. This device, which we now call a telescope, revealed to Galileo things that no human being had ever seen before. He saw that the moon was not a smooth sphere but a rugged world of mountains and craters. He saw that Jupiter was accompanied by 4 smaller bodies that circled around it, moons of its own, demonstrating that not everything in the cosmos revolved around the Earth. He saw that Venus went through phases like our moon, growing from crescent to full and back again, which could only be explained if Venus was circling the Sun. And he saw that the Milky Way, that faint river of light stretching across the summer sky, was composed of countless individual stars, far more than anyone had ever imagined, too many to count, crowded together in a luminous haze. Galileo published these discoveries in a small book called Sidereus Nuncius, The Starry Messenger, and copies of this work made their way across Europe, carried by couriers and merchants and scholars, until one reached Kepler in Prague. Kepler read it with great excitement and wrote a long response, published later that same year of 1610, which he called Dissertatio cum Nuncio Siderio, or Conversation with the Starry Messenger. In this work, Kepler praised Galileo's discoveries and considered their implications, and in the course of this consideration, he posed a question that seems, on the surface, almost childishly simple, the kind of question that a small child might ask and that an adult might be tempted to dismiss with a wave of the hand, not realizing that the question contains within it depths that the greatest minds of the age could not fathom. The question was this: if the universe is infinite, as some philosophers had suggested, and if the stars are distributed throughout this infinite space more or less uniformly, as one might reasonably suppose, then when you look up at the night sky, your line of sight must eventually, no matter which direction you look, encounter a star. Not just one star, but in fact every possible line of sight, extending outward from your eye in every direction, must eventually terminate upon the surface of some distant sun. And if this is the case, then the entire sky, every part of it without exception, should be covered by stars, overlapping and crowding together until there is no dark space left between them. The sky, in other words, should not be dark at all. It should be blazingly bright, as bright as the surface of the sun itself, a continuous sheet of stellar fire covering the heavens from horizon to horizon, with no relief, no shadow, no darkness anywhere. But this is manifestly not what we observe. When night falls and the sun sinks below the horizon, the sky does not blaze with unendurable light. Instead, it grows dark, and the stars appear as scattered points of light against a vast black backdrop, each one separated from its neighbors by expanses of empty darkness. The darkness between the stars is not merely an apparent darkness, not merely a dimness that better eyes or better instruments might resolve into more light. It is a genuine absence, a void, a blackness that seems to have no source and no explanation, at least not within the framework of an infinite universe uniformly populated with stars. Kepler understood this problem with perfect clarity, and he saw that it pointed to a profound conclusion. The universe, he reasoned, could not be infinite. If it were infinite and uniformly filled with stars, the sky would be bright, but the sky is dark, and therefore the universe must be finite. There must be an end to it, a boundary, a dark wall beyond which there are no more stars, only emptiness, only the void that we perceive as the black background against which the stars are set. Kepler imagined the cosmos as a kind of vast room, immense beyond human comprehension but not without limits, bounded by this shell of darkness, this cosmic enclosure that contained all the stars and planets and kept them from spreading infinitely outward. This conclusion was wrong, as we now understand, but it was wrong in an interesting and important way. Wrong because Kepler did not have access to the knowledge that would eventually provide the true explanation, knowledge about the finite speed of light, about the finite age of the universe, about the expansion of space itself, concepts that would not be developed for another 300 years. What matters is not that Kepler's answer was incorrect, but that his question was correct. that he saw the problem clearly and articulated it precisely, that he recognized the darkness of the night sky as something requiring explanation rather than something to be taken for granted. In the years that followed, Kepler continued his work, eventually leaving Prague after the death of Rudolf II and the political upheavals that followed, settling for a time in Linz, where he served as a district mathematician and continued his astronomical researches. He corresponded with Galileo, though the two men never met in person, exchanging letters across the Alps, discussing telescopes and planets and the implications of their discoveries for the ancient understanding of the cosmos. Kepler sent Galileo a copy of his book and received a warm reply, though Galileo was sometimes slow to respond and did not always give Kepler the credit he deserved for his theoretical insights. During these later years, Kepler's life was shadowed by the terrible accusation of witchcraft brought against his mother, Caterina. She was arrested in 1620 and imprisoned for over a year, threatened with torture, subjected to an ordeal that was as much about local grudges and superstition as it was about any actual wrongdoing. Kepler devoted enormous energy to her defense, writing legal briefs, traveling back and forth, neglecting his other work to fight for her freedom. She was eventually released, though she died only a few months later, worn out by the experience. It is remarkable to consider that during this same period, while dealing with this personal nightmare, Kepler continued to think about the stars, continued to ponder the great questions of cosmology, continued to work on his astronomical tables, which would be published after his death and would remain the most accurate predictions of planetary positions for nearly a century. He died in 1630, in the city of Regensburg, while traveling to collect money owed to him, still seeking the financial security that had eluded him throughout his life. He was buried in a churchyard that was later destroyed during the 30 Years' War, and his grave has been lost, though his ideas have not been lost, and his question, the simple profound question about the darkness of the night sky, lived on, waiting for future generations to take it up again, to struggle with it, to propose their own answers, until at last, in the fullness of time, the true explanation would emerge, built from discoveries that Kepler could never have anticipated, discoveries about the nature of the universe itself. And so we find ourselves now moving forward through time, past the age of Newton and his laws of motion, past the great catalogues of stars being assembled across Europe, forward into the early decades of the 19th century, to the city of Bremen in the north of Germany, where a physician by the name of Heinrich Wilhelm Olbers would give this ancient puzzle its lasting name, though he was certainly not the first to consider it, and though his proposed solution would eventually prove to be incorrect. His careful mathematical treatment of the problem ensured that it would forever after be known as the paradox of Olbers, or simply Olbers' paradox, a phrase that has appeared in countless textbooks and astronomical papers in the nearly 2 centuries since he first set his thoughts to paper. Heinrich Wilhelm Olbers was born in the year 1758 in the village of Arbergen, not far from Bremen, into a world still illuminated by candlelight and oil lamps, a world where the night sky was darker and more present than it is for most of us today. He trained as a physician and practiced medicine in Bremen for most of his adult life, tending to the ordinary ailments and injuries of his patients during the daylight hours. But his true passion, the work that occupied his evenings and his thoughts, was the study of the heavens. He constructed an observatory in the upper floors of his home, and there, night after night, he turned his telescope toward the stars with a patience and dedication that characterized so many of the great amateur astronomers of that era. It is worth pausing here to note that Olbers was not merely a casual observer of the sky, but a serious contributor to astronomical knowledge. In the year 1802, he discovered the asteroid Pallas, only the second such small body ever identified in the region between Mars and Jupiter, following the discovery of Ceres just a year earlier by the Italian astronomer Giuseppe Piazzi. Then, in 1807, Olbers discovered Vesta, the brightest of all the asteroids and one that can occasionally be glimpsed with the naked eye under favorable conditions. These discoveries alone would have secured his place in the history of astronomy, but it is for a different contribution entirely, a question rather than a discovery, that his name is most often remembered today. In the year 1823, when Olbers was 65 years old and had spent decades observing the night sky from his Bremen observatory, he published a paper addressing a problem that had quietly troubled astronomers and natural philosophers for generations. The problem was simply this: if the universe is infinite in extent, and if it has existed for an infinite span of time, and if stars are distributed more or less uniformly throughout its endless reaches, then why is the night sky dark? The reasoning behind this question can be followed step by careful step, and it is perhaps best if we work through it slowly together, allowing each piece to settle into place before moving on to the next. Let us begin by considering what it means for the universe to be infinite. If space extends forever in all directions, with no boundary and no edge, and if stars are scattered throughout this infinite expanse with roughly the same density everywhere, then no matter which direction you choose to look, your line of sight will eventually intersect with the surface of a star. It may be a star very far away, unimaginably distant, but in an infinite universe filled with stars, there will always be a star somewhere along any line you draw outward from your eye. Now, you might reasonably object that stars become dimmer as they get farther away, and this is absolutely true. The brightness of a star diminishes according to a principle known as the inverse square law, which states that if you double your distance from a light source, its apparent brightness falls to 1/4 of what it was. Triple the distance, and the brightness falls to 1/9. Move 10 times farther away, and the star appears only 1/100th as bright. This is a straightforward consequence of geometry, of the way light spreads out as it travels through space, and it applies equally to stars, candles, street lamps, and any other source of illumination you might care to consider. So the inverse square law tells us that distant stars are dim, and this seems at first to resolve the puzzle. Surely, you might think, the stars at vast distances contribute so little light that their combined effect is negligible. But here is where the mathematics of infinity introduces its peculiar and counterintuitive effects. If we imagine space divided into concentric shells centered on the Earth, like the layers of an onion extending outward forever, then each shell that is twice as far away contains 4 times as many stars, because the volume of the shell grows with the square of the distance. The stars in that more distant shell are each 4 times dimmer, following the inverse square law, but there are 4 times as many of them, and so the total light contributed by that shell is exactly the same as the shell closer in. And the shell beyond that, twice as far again, also contributes the same total amount of light. And so on, through shell after shell extending to infinity. When you sum up the contributions from infinitely many shells, each adding the same finite amount of light, the total becomes infinite. In such a universe, the entire sky would blaze with the brightness of stellar surfaces, every point in every direction filled with the light of overlapping stars. The night sky would not merely be bright, it would be as bright as the surface of an average star, which is to say roughly 5,500 degrees Celsius, the temperature of the visible surface of our own Sun. The Earth would be bathed in radiation so intense that no life as we know it could exist, and indeed, no solid matter could survive. This is the essence of the paradox, the stark contradiction between what the mathematics of an infinite, static, eternal universe predicts and what we actually observe when we step outside on a clear night and see darkness pricked with scattered points of light. Olbers was not, in fact, the first person to notice this troubling discrepancy, and it would be unfair to those who came before him to suggest otherwise. The great English astronomer Edmund Halley, best known today for the comet that bears his name, touched upon this problem in a paper presented to the Royal Society in 1720, more than a century before Olbers' own publication. Halley noted that if stars were distributed throughout infinite space, their light ought to fill the sky entirely, and he speculated on possible explanations without arriving at a satisfactory resolution. His treatment of the matter was brief and somewhat tentative, and it did not attract the sustained attention that the problem perhaps deserved. Then, in 1744, a Swiss astronomer named Jean-Philippe Lois de Chessos addressed the paradox with considerable mathematical sophistication in a work primarily devoted to the study of comets. De Chessos worked through the geometry of overlapping stellar shells much as we have just done, and he arrived at the same disturbing conclusion, that in an infinite universe uniformly populated with stars, every line of sight should terminate at a stellar surface, and the sky should be uniformly brilliant. He proposed that light might somehow be absorbed or attenuated as it traveled through space, growing weaker with distance beyond what the inverse square law alone would predict, and this absorption might explain why we do not see the infinite brightness that the mathematics seem to demand. Olbers, working independently some 80 years later, arrived at a similar proposal. He suggested that the interstellar medium, the space between the stars, might contain some form of matter, perhaps a thin dust or gas, that would absorb the light of distant stars and prevent it from reaching us. In this way, the more distant shells of stars would contribute progressively less light, not merely because of the inverse square law but because their light would be filtered and diminished by the intervening material. If this absorption were strong enough, it might explain why the night sky is dark despite the presumed infinity of stars. This explanation seemed reasonable at the time, and it satisfied many who encountered it. Interstellar space, after all, is not perfectly empty. We know today that it contains sparse clouds of gas and microscopic grains of dust, and this material does indeed absorb and scatter starlight to some degree. But there is a fundamental flaw in Olbers' solution, one that was not fully appreciated until later in the 19th century and into the 20th. The problem is this: any material that absorbs energy must itself heat up, and as it heats, it will begin to radiate energy of its own. Consider a sheet of metal placed near a fire. At first it absorbs the heat, growing warmer and warmer, but eventually it reaches a temperature at which it begins to glow, first a dull red, then orange, then yellow, radiating light and heat back into its surroundings. The dust grains floating in interstellar space would behave in much the same way. If they were truly absorbing the light of infinitely many stars, they would heat up and keep heating until they reached thermal equilibrium with their surroundings, at which point they would radiate energy at the same rate they absorbed it. The dust might block the visible light of the stars, but it would simply re-emit that energy at different wavelengths, and the total radiation filling space would remain just as intense. You cannot hide infinite energy behind a curtain of dust, because the curtain itself will eventually glow with all the energy it has absorbed. And so Olbers' proposed solution, while clever, could not be the true answer. The paradox remained, attached now to his name but still unresolved, a puzzle that would require entirely new ways of thinking about the cosmos before it could be properly understood. Olbers himself continued his astronomical observations and his medical practice until his death in 1840 at the age of 81, leaving behind a legacy of asteroid discoveries and a question that would outlive him by more than a century before its resolution became clear. The situation, then, stood roughly as follows by the middle of the 19th century. A number of thoughtful observers had noticed that the darkness of the night sky posed a genuine problem for the prevailing conception of the universe as infinite, eternal, and static. Various solutions had been proposed, including the absorption of light by interstellar matter, but none had proven fully satisfactory upon careful examination. The paradox was well defined and well known, at least among those who concerned themselves with such foundational questions about the nature of the cosmos, but a convincing resolution remained elusive. It is worth taking a moment to appreciate the significance of this situation. Here was a question that any child might ask, a question that arises naturally from simply looking up at the night sky and wondering why it is not brighter. And yet this simple question, when pursued rigorously and honestly, led directly to a profound contradiction at the heart of the accepted model of the universe. Either the universe was not infinite, or it was not eternal, or stars were not uniformly distributed, or something else entirely was at play that had not yet been imagined. The darkness of the night sky was not merely a curiosity or an aesthetic observation. It was a clue, perhaps the most profound clue that nature had offered, pointing toward truths about the cosmos that would take many more decades to uncover. But for now, in the early and middle 19th century, the paradox simply sat there, named after a kindly German physician who had done his best to solve it and failed, waiting patiently for future generations to find the key that would unlock its meaning and transform our understanding of space, time, and the universe itself. And so we arrive now at a new century, and a new landscape of understanding, where the tools of astronomy had grown large enough and sensitive enough to peer deeper into the cosmos than anyone before had managed, and where the quiet work of patient observers would eventually overturn everything that had been assumed about the nature of the universe itself, and about its size, and about whether it sat still in eternal unchanging majesty or whether it moved and breathed and stretched in ways no one had quite anticipated. The place where much of this transformation occurred was a mountain in Southern California, above the city of Pasadena, where the air was often clear and the seeing was good, and where a great observatory had been constructed through the vision and persistence of George Ellery Hale, who had a remarkable gift for convincing wealthy benefactors to fund ever larger telescopes, each one surpassing the last, each one opening new windows onto the distant reaches of space. This was Mount Wilson Observatory, and by the 1920s it housed the largest telescope in the world, a reflecting telescope with a primary mirror 100 inches in diameter, which is about 2.5 meters for those who prefer metric units, and this mirror had been cast and polished and figured with extraordinary care, and it gathered so much light that objects previously invisible or barely glimpsed could now be studied in detail, their spectra analyzed, their distances estimated, their true nature slowly revealed through the accumulation of photographic plates and careful measurement. The telescope was called the Hooker telescope, named for John D. Hooker, a Los Angeles businessman who had provided the funds for its construction, and it had seen first light in 1917. And in the years that followed, it became the instrument through which some of the most profound discoveries in the history of astronomy would be made. Discoveries that would reshape our understanding of where we are and what surrounds us, and whether the cosmos has a history or merely an eternal present. Among the astronomers who came to use this great telescope was Edwin Hubble, a man of considerable intelligence and equally considerable self-regard, who had studied law at Oxford as a Rhodes Scholar before turning to astronomy, and who carried himself with a certain formality and an affected English accent that his colleagues found either charming or irritating depending on their disposition, but whose observational work was meticulous and whose conclusions, whatever one thought of his personality, would prove to be among the most important in the entire history of science. Hubble had arrived at Mount Wilson in 1919, just after the end of the First World War, in which he had served, and he set about studying the objects that were then called spiral nebulae, those faint fuzzy patches of light that showed, when examined through sufficiently powerful telescopes, a distinctive spiral structure, with arms of luminous material winding outward from a central core, and which had been the subject of considerable debate for many years. The question was whether these spiral nebulae were relatively small objects within our own Milky Way galaxy, perhaps clouds of gas or newly forming solar systems, or whether they were vastly larger and vastly more distant, perhaps entire galaxies in their own right, island universes comparable in size to our own stellar system but separated from us by almost unimaginable gulfs of space. This debate, sometimes called the Great Debate, had been argued formally in 1920, with respected astronomers on both sides presenting evidence and counter-evidence, and it had not been conclusively resolved, because the distances to these objects were simply too uncertain, the methods of measurement too imprecise, the data too sparse to settle the matter definitively. Hubble set about trying to resolve this question using the great light-gathering power of the Hooker telescope, and in 1923 and 1924 he succeeded in identifying individual stars within the Andromeda Nebula, which was one of the largest and brightest of the spiral nebulae, and among these stars he found several that belonged to a special class called Cepheid variables, which are stars that brighten and dim in a regular periodic fashion, and whose period of variation, the time it takes to go from bright to dim and back to bright again, is directly related to their intrinsic luminosity. This relationship, discovered by Henrietta Swan Leavitt at Harvard College Observatory some years earlier, provided a cosmic yardstick, a way of determining how far away a Cepheid variable must be, because if you know how intrinsically bright a star truly is, and you measure how bright it appears to be from Earth, you can calculate how much distance must separate you from it, since apparent brightness decreases with the square of distance, a simple geometric fact that astronomers call the inverse square law. Using this method, Hubble calculated that the Andromeda Nebula was approximately 900,000 light-years away, which placed it far, far beyond the boundaries of our own Milky Way galaxy, which was thought to be perhaps 100,000 light-years across, and this meant that the spiral nebulae were not small nearby objects at all, but were instead separate galaxies, each one containing billions of stars, each one a vast island of matter floating in the dark ocean of intergalactic space. This discovery, announced in 1924, expanded the known universe by an almost incomprehensible factor, transforming it from a single galaxy surrounded by darkness into a cosmos populated by countless galaxies, each one a city of stars, stretching outward in all directions as far as telescopes could see. But Hubble did not stop there, and in the years that followed he turned his attention to another question, which was whether these distant galaxies were moving relative to us, and if so, in what directions and at what speeds. And it was in pursuing this question that he made his second great discovery, the one that would eventually provide part of the answer to Olbers' paradox, though Hubble himself seems not to have been particularly interested in that old puzzle. To measure the motion of distant objects, astronomers use a phenomenon called the Doppler effect, which you may have noticed in everyday life when an ambulance or a police car passes by with its siren wailing, because as the vehicle approaches, the sound waves are compressed slightly, making the pitch of the siren seem higher, and as it recedes, the sound waves are stretched out, making the pitch seem lower, and this shift in pitch tells you something about how fast the vehicle is moving and in which direction. Light behaves in a similar way, though of course light is not a sound wave but an electromagnetic wave, and when a source of light is moving toward you, the light waves are compressed to shorter wavelengths, shifting the light toward the blue end of the spectrum, and when a source of light is moving away from you, the light waves are stretched to longer wavelengths, shifting the light toward the red end of the spectrum, and this shift is called blue shift or red shift respectively, and it can be measured with great precision by examining the spectral lines of the light source. Those characteristic patterns of bright or dark lines that appear when light is passed through a prism or a diffraction grating and spread out into its component wavelengths. Each chemical element produces a unique pattern of spectral lines, a kind of fingerprint that identifies its presence, and these patterns are the same whether the element is in a laboratory on Earth or in a star millions of light-years away. But if the source is moving toward or away from us, all the lines will be shifted slightly from their normal positions, and the amount of shift tells us the velocity of the source along our line of sight. Now, Hubble was not the first to measure redshifts of spiral nebulae, because that work had already been done, and done very well, by an astronomer named Vesto Slipher, who worked at Lowell Observatory in Flagstaff, Arizona, and who had been taking spectra of spiral nebulae since 1912, using a much smaller telescope than the one at Mount Wilson, and finding, through painstaking work over many years, that almost all of them showed redshifts rather than blue shifts. Slipher had published his results between 1912 and 1917. Showing that the spiral nebulae were moving away from us at considerable velocities, some as high as several hundred kilometers per second. And this was a remarkable finding, though its full significance was not immediately appreciated, because at the time it was still unclear whether these nebulae were within our galaxy or beyond it, and their motions could perhaps be explained as ordinary stellar velocities if they were nearby objects. But once Hubble had established that the spiral nebulae were in fact distant galaxies, the redshift measurements took on new meaning, and Hubble, working with a colleague named Milton Humason, who was a skilled observer and spectroscopist, began collecting more redshift data for galaxies at various distances, combining Slipher's earlier measurements with new ones of his own, and plotting the results on a graph with distance on one axis and velocity on the other. What emerged from this analysis, published by Hubble in 1929, was a striking relationship, a pattern so simple and so unexpected that it seemed almost too elegant to be true, which was that the velocity at which a galaxy recedes from us is directly proportional to its distance from us, so that a galaxy twice as far away is moving away twice as fast, and a galaxy 10 times as far away is moving away 10 times as fast, and this proportionality holds across all the galaxies measured, at least within the uncertainties of the data. This relationship is now called Hubble's law, and the constant of proportionality, which relates velocity to distance, is called the Hubble constant. though the value Hubble originally calculated was considerably higher than the modern accepted value, because his distance estimates contained systematic errors that were not corrected until many years later. The velocities Hubble measured ranged up to about 1,000 kilometers per second for the most distant galaxies in his sample, which were tens of millions of light-years away. And these numbers, while large by earthly standards, were merely hints of the much greater velocities that would later be measured for galaxies at much greater distances, velocities that approach a significant fraction of the speed of light itself. Now, what does it mean that all galaxies, or nearly all, are moving away from us, and that the farther they are, the faster they recede? And might this suggest that we occupy some special central position in the universe, from which everything else is fleeing, as if we were the point of some cosmic explosion? The answer, as it turns out, is no. We do not occupy any special position, because the relationship Hubble discovered would look exactly the same from any other galaxy in the universe, which is to say that observers in Andromeda or in the Virgo cluster or in any other distant galaxy would also see all other galaxies receding from them, with velocities proportional to distance, and they would be equally justified in thinking themselves at the center, which means that there is no center, or rather that every point is equally the center, which is a difficult concept to grasp but which follows naturally from the mathematics of an expanding space. It is not that the galaxies are moving through space away from us, like shrapnel from an explosion, but rather that space itself is expanding, carrying the galaxies along with it, so that the distance between any two galaxies increases over time, not because they are traveling through space but because there is simply more space between them than there was before, as if the fabric of the cosmos were stretching in all directions simultaneously. This idea of an expanding universe had actually been proposed 2 years before Hubble's famous paper, in 1927, by a Belgian priest and physicist named Georges Lemaitre, who had derived the expansion mathematically from Einstein's equations of general relativity and had even calculated an early estimate of the expansion rate, though his paper, published in French in a Belgian journal, did not receive wide attention at the time and was not translated into English until several years later. Lemaitre had taken Einstein's theory of general relativity, which describes how matter and energy curve the fabric of spacetime, and had found a solution in which the universe was not static but dynamic, either expanding or contracting, and he had recognized that the redshift measurements of spiral nebulae were consistent with an expanding universe, and he had written about this with clarity and insight, though history has tended to credit Hubble with the discovery, partly because Hubble's data were more extensive and partly because Hubble was working at a more prominent institution and published in a more widely read journal. Einstein himself had initially resisted the idea of an expanding universe, even though his own equations permitted it, because like most scientists of his era, he assumed that the universe must be static and eternal. And to achieve this in his theory, he had introduced an additional term called the cosmological constant, which provided a kind of repulsive force that could balance the attractive force of gravity and hold the universe in equilibrium. When the evidence for expansion became overwhelming, Einstein reportedly said that the cosmological constant was his biggest blunder, because he had missed the opportunity to predict the expansion of the universe before it was observed, which would have been yet another triumph for his theory, though in fact the cosmological constant has made a kind of comeback in modern cosmology, where it is associated with dark energy and the accelerating expansion of the universe, so perhaps it was not such a blunder after all. For our purposes, lying here quietly and thinking about the darkness of the night sky, the expansion of the universe offers a partial answer to Olber's paradox, Because if distant galaxies are receding from us, then the light they emit is redshifted to longer wavelengths, and for very distant galaxies receding at very high velocities, this redshift can be substantial, shifting visible light into the infrared or even the microwave portion of the spectrum, where our eyes cannot detect it. So some of the light that would otherwise reach us and brighten the night sky has been stretched beyond visibility, its energy diminished, its color shifted to wavelengths we cannot see without special instruments, and this means that the night sky appears darker than it would in a static universe, because much of the light from distant sources has been redshifted away. This is indeed part of the solution, a meaningful piece of the puzzle, but it is not by itself sufficient to fully resolve Olbers' paradox, because even accounting for redshift, if the universe were infinitely old and infinitely large and filled uniformly with stars and galaxies that had been shining forever, the accumulated light would still be enough to make the sky bright, just at longer wavelengths, and the energy would still be there, still warming the cosmos, still filling every corner of space. The full resolution requires something more, something that the expanding universe hints at but does not by itself prove, and that something is the recognition that the universe has not existed forever, that it had a beginning, that there is only a finite time during which light has been able to travel from distant sources to our eyes, and this limitation, this cosmic horizon beyond which we simply cannot see because light has not had enough time to reach us, is the final piece needed to explain why the night sky is dark. But that realization came later, through the further development of cosmological theory, through the refinement of observations, through the gradual construction of what we now call the Big Bang model, and we need not hurry toward it, because there is time enough to let these ideas settle, to let the redshifts and the expanding space and the receding galaxies drift gently through the mind like stars wheeling slowly overhead on a long clear night. And so we come now to a rather profound realization, one that emerged slowly through the 20th century and continues to shape our understanding of the cosmos in ways both subtle and far-reaching. The observable universe, it turns out, possesses a boundary, though not the sort of boundary one might initially imagine. It is not a wall of stone or a fence of starlight marking the edge of all that exists. It is not a place where space simply stops, where matter gives way to some fundamental void or emptiness beyond. The boundary of our observable universe is not a boundary in space at all, but rather a boundary in time, and this distinction, though it may seem merely philosophical at first hearing, carries with it consequences that directly address the ancient puzzle of why the night sky appears dark. To understand this temporal boundary, we must consider what happens when we look outward into the cosmos. When we observe a distant galaxy, we are not seeing that galaxy as it exists at this present moment. We are seeing it as it existed when the light now reaching our eyes first departed from its stars. Light travels extraordinarily quickly by terrestrial standards, covering nearly 300,000 kilometers in a single second. Yet the distances between galaxies are so vast, so incomprehensibly enormous, that even at this tremendous speed, light requires millions or billions of years to traverse the separations between them. A galaxy 1 billion light-years distant appears to us as it was 1 billion years ago. A galaxy 10 billion light-years distant appears as it was 10 billion years ago. And so, in looking outward across space, we are necessarily looking backward through time, and every increase in distance corresponds to an equal journey into the past. This relationship between distance and time means that if the universe itself has a finite age, then there must exist a maximum distance from which any light could possibly have reached us by now. Beyond this distance, There has simply not been sufficient time since the beginning of the universe for light to have made the journey. This represents not an edge in space, where the universe physically ends, but rather an edge in time, a horizon beyond which we cannot see because the universe itself did not yet exist. And this horizon, this temporal boundary to our observations, plays a crucial role in explaining the darkness of the night sky, though the full understanding of its nature required discoveries that would not come until the latter half of the 20th century. In the year 1964, in the township of Holmdel in the state of New Jersey, two physicists named Arno Penzias and Robert Wilson were engaged in work that would ultimately earn them the Nobel Prize, though they had no inkling of this at the time, and their discovery would arrive not through careful theoretical prediction on their part, but through what initially appeared to be a frustrating technical problem that refused to be solved. Penzias and Wilson were employed at Bell Telephone Laboratories, and they were attempting to use a rather unusual piece of equipment for radio astronomy observations. This equipment was a large horn antenna, standing some 20 feet in height, which had originally been constructed for communication experiments involving early satellites. The antenna's horn reflector design made it particularly well suited for detecting faint radio signals, and Penzias and Wilson had hoped to use it for studying radio emissions from the halo of our own Milky Way galaxy. However, upon beginning their observations, the two physicists encountered a persistent problem. No matter which direction they pointed the antenna, no matter what time of day or night they made their measurements, no matter what season of the year, they detected a faint but constant hiss of radio noise that they could not account for. This noise corresponded to a temperature of approximately 3.5 Kelvin, meaning it matched the radiation that would be emitted by an object only 3.5 degrees above absolute zero. The signal was far too constant and too uniform to be coming from any specific astronomical source. It appeared to pervade all of space equally, arriving from every direction with precisely the same intensity, and this ubiquity made its origin deeply puzzling. Penzias and Wilson, being careful experimentalists, devoted considerable effort to eliminating possible sources of interference or error. They examined every component of their antenna system. They tested their electronics repeatedly. They even noticed that a pair of pigeons had taken up residence within the horn of the antenna and had deposited what the physicists delicately described in their notes as a white dielectric material upon the antenna's surfaces. Suspecting that these deposits might somehow be responsible for the mysterious noise, Penzias and Wilson carefully cleaned the antenna and relocated the pigeons to a distant location, though the birds, displaying the homing instincts common to their species, promptly returned and had to be dealt with through more permanent means. Yet even after this thorough cleaning, and even after checking every conceivable source of instrumental error, the faint hiss persisted, constant and uniform and completely unexplained. Meanwhile, at Princeton University, less than an hour's drive from the Bell Labs facility in Holmdel, a small group of physicists were engaged in work that would prove to be intimately connected to the mystery that Penzias and Wilson were confronting, though neither group was initially aware of the other's activities. The Princeton team included Robert Dicke, an experimental physicist of considerable ingenuity, and a young theorist named Jim Peebles. This group had been considering the theoretical consequences of an expanding universe that had begun in an extremely hot, dense state, and they had calculated that if the universe had indeed originated in such a manner, then the radiation present in that early fireball should still exist today, though cooled and stretched by the expansion of space to the point where it would appear as faint microwave radiation pervading all of the cosmos. Dickey and his colleagues were in the process of constructing their own antenna specifically designed to search for this predicted radiation when they learned of the unexplained signal that Penzias and Wilson had been struggling to eliminate. The connection was soon made, and its implications were recognized as profound. The faint, persistent hiss that Penzias and Wilson had detected was not instrumental noise, nor was it caused by pigeon droppings or any other mundane source of interference. It was the cooled remnant of the primordial fireball, the afterglow of the Big Bang itself, still permeating all of space some 14 billion years after the event that had produced it. This radiation, which came to be known as the cosmic microwave background, represented the oldest light in the universe, the most ancient electromagnetic radiation that it is possible to observe, and its discovery provided direct evidence that the universe had indeed begun in an extremely hot, dense state and had been expanding and cooling ever since. To understand why the cosmic microwave background represents a boundary in time, we must consider the conditions that prevailed in the early universe. In the first few 100,000 years following the Big Bang, the universe was filled with a plasma of charged particles, primarily protons and electrons, along with tremendous quantities of electromagnetic radiation. In a plasma, free electrons scatter photons with great efficiency, much as fog scatters the light from a torch, and this scattering prevents light from traveling any significant distance in a straight line. The early universe, therefore, was opaque, filled with light yet incapable of transmitting that light across any meaningful distance, and any observer within such a universe, had such an observer been possible, would have been unable to see beyond their immediate surroundings, as thoroughly obscured as a person lost in a dense and all-encompassing fog. This opacity persisted for approximately 380,000 years following the Big Bang. During all of that time, the universe continued to expand and to cool, and eventually a threshold was crossed. The temperature dropped sufficiently that protons and electrons could combine to form neutral hydrogen atoms, a process that physicists refer to as recombination, though this terminology is somewhat misleading since the protons and electrons had never been combined previously. With the electrons now bound within atoms rather than roaming freely through space, the scattering of photons largely ceased, and the universe rather suddenly became transparent. Light that had been trapped, endlessly scattered, endlessly redirected, was now free to travel unimpeded across the cosmos. This transition from opacity to transparency, from a fog of charged particles to a clear expanse of neutral atoms, is sometimes called the surface of last scattering, for it represents the last moment at which the primordial light was scattered before beginning its long journey across the universe. And it is this surface, this moment of transition occurring approximately 380,000 years after the Big Bang, that we observe when we detect the cosmic microwave background radiation. When we measure this ancient light with our instruments, we are not seeing individual objects or specific structures, but rather a kind of wall, a boundary in time beyond which the universe was opaque and from which no earlier light can reach us. This is the edge of the observable universe, and it is an edge in time rather than in space. In 1989, the Cosmic Background Explorer satellite, known by its abbreviation COBE, was launched with the purpose of studying the cosmic microwave background with unprecedented precision. Earlier measurements from the ground and from high-altitude balloons had established the existence and basic properties of this radiation, but the COBE satellite, orbiting above the interference of Earth's atmosphere, was able to map the microwave sky in extraordinary detail. What the satellite revealed was that the cosmic microwave background is astonishingly uniform, appearing nearly identical in all directions to a precision that initially seemed almost impossible. Yet within this uniformity, COBE detected subtle variations, tiny fluctuations in temperature amounting to only 1 part in 100,000. These minuscule variations, these faint ripples in the otherwise smooth background, represented the seeds from which all later cosmic structure would grow, the slight overdensities that would eventually collapse under their own gravity to form the first galaxies and clusters of galaxies. The cosmic microwave background, then, is not merely an interesting curiosity of observational cosmology. It provides a fundamental explanation for a portion of the darkness we observe when we look up at the night sky. The spaces between the stars, the dark gaps between the visible galaxies, are not truly empty. They are filled with this ancient light, the cooled and stretched remnant of the primordial fireball, radiation that was once blindingly bright and is now so thoroughly redshifted by the expansion of the universe that it has passed entirely beyond the range of visible light into the long wavelengths of the microwave spectrum. If our eyes were sensitive to microwaves rather than visible light, the night sky would not appear dark at all. It would glow uniformly in all directions with this ancient radiation, a faint but omnipresent illumination marking the boundary between the observable universe and the opaque epoch that preceded it. This is the resolution, or at least part of the resolution, to the paradox that puzzled astronomers for so many centuries. The darkness of the night sky is not evidence of cosmic emptiness, nor does it result simply from the finite number or finite brightness of stars. It results from the finite age of the universe itself, from the fact that light requires time to travel across space, and from the expansion that stretches ancient light beyond the threshold of visibility. The darkness we see is not an absence of light but rather the presence of the oldest light possible, light so ancient and so stretched that it has become invisible to eyes evolved to detect only a narrow band of the electromagnetic spectrum. The night sky is filled with this primordial glow, and the darkness we perceive is merely a limitation of our perception, a reminder that the universe speaks in many frequencies and that most of its messages pass by us unheard and unseen. And so we arrive, as the night settles deeper around us, at the true answer to this ancient question, the resolution that had waited patiently through centuries of speculation and calculation and philosophical wondering, hidden in plain sight above every human head that ever tilted back to look at the stars. The darkness of the night sky, that velvet absence between the scattered points of light, is not a mystery of missing stars or invisible matter or some peculiar absorption of light by intervening substances. It is something far more fundamental, far more quietly astonishing in its simplicity. The universe, you see, has a birthday. This is perhaps the most important single fact that distinguishes our modern understanding of the cosmos from all the cosmologies that came before it, and it is worth letting that idea settle gently into your thoughts as you rest. The universe is not infinitely old. It did not stretch backward through time without beginning, without origin, without a first moment when space and light and matter came into being. Instead, there was a time, measured with remarkable precision by instruments we have sent beyond our atmosphere, when everything began. And that beginning occurred approximately 13.8 billion years ago, give or take a few tens of millions of years, which in cosmic terms is really quite a narrow margin of uncertainty. The measurement of this age, this birthday of all that exists, was accomplished most precisely by a spacecraft called Planck, named after the German physicist Max Planck, who had contributed so much to our understanding of how light and energy behave. The European Space Agency launched this satellite in May of 2009, sending it to a point in space about 1.5 million kilometers from Earth, where it could observe the faint afterglow of the universe's earliest light without interference from our planet or its atmosphere. For several years, Planck drifted in the darkness, its instruments cooled to temperatures colder than the void of deep space, listening to the whisper of radiation that has been traveling toward us since the cosmos was only a few 100,000 years old. The results of this patient listening were published in 2013, and they told us, with a precision that would have astonished earlier generations of astronomers, that the universe began 13.8 billion years ago. This number was not a guess, not an approximation based on philosophical reasoning, but a measurement derived from the patterns in that ancient light, patterns that revealed how quickly the early universe had expanded, how much matter it contained, and how long it had been traveling through an ever-growing cosmos to reach our instruments. Now, to understand why this cosmic birthday answers the question of the dark night sky, we must consider something about the nature of light itself, something so fundamental that we often forget to think about it consciously. Light, the electromagnetic radiation that carries images of distant stars to our eyes, travels at a finite speed. It is the fastest thing in the universe. Nothing with mass can ever match or exceed its velocity, and yet it does not arrive instantaneously. Light moves through the vacuum of space at precisely 299,792 kilometers every second, a speed so great that it could circle the Earth more than 7 times in a single heartbeat, and yet a speed that is finite, measurable, bounded. This means that when we look at a star, we do not see it as it is now, in this present moment, but as it was when the light we are receiving left its surface. The light from our own sun takes about 8 minutes to reach us, so we see the sun as it was 8 minutes ago, a delay so brief that it makes no practical difference to our daily experience. But the light from the nearest star beyond our sun, a small red star called Proxima Centauri, takes more than 4 years to cross the distance between us. When we look at that faint point of light, we are looking backward through time, seeing the star as it existed when the light began its journey, not as it exists in the moment of our observation. Extend this principle outward, to more distant stars and galaxies, and the delays become vast. The light from the Andromeda galaxy, our nearest large galactic neighbor, has been traveling for approximately 2.5 million years to reach your eyes when you look at it on a clear night. We see Andromeda not as it is, but as it was when our distant ancestors were taking their first uncertain steps on the African savanna, before any human had ever gazed up and wondered about the nature of the heavens. And here we find the resolution to Olbers' paradox, the answer to why the night sky is dark in a universe that may indeed be infinite in extent. Because the universe has a finite age, because it came into being 13.8 billion years ago, there is a limit to how far we can see. We can only observe objects whose light has had enough time to reach us since the beginning of everything. Beyond that distance, there may be more stars, more galaxies, more light being generated at this very moment, but we cannot see any of it, because the light has not yet arrived. It is still on its way, crossing the expanding void between its origin and our eyes, and it will not reach us for millions or billions of years yet to come. This creates what astronomers call the observable universe, a sphere centered on Earth not because our planet is special or central, but simply because we are the observers, looking outward in all directions at light that has been traveling toward us for varying amounts of time. The radius of this observable sphere is determined by the age of the universe and the speed of light. But the calculation is complicated slightly by a factor that would have astonished astronomers of earlier centuries, namely that space itself has been expanding throughout all those billions of years, stretching like the surface of a balloon being slowly inflated. Because of this expansion, the observable universe has a diameter of approximately 93 billion light-years, which seems paradoxical at first, larger than what 13.8 billion years of light travel should allow. But this is because the space between distant objects and ourselves has continued to stretch even as their light was making its journey toward us. The galaxies that emitted the oldest light we can see were much closer to us when that light began its journey, and have been carried farther away by the expansion of space during the billions of years that the light was in transit. So the universe we can observe is larger than a simple multiplication of age and light speed would suggest, but it is still finite, still bounded, still limited by the fundamental constraint that nothing, not even information, can travel faster than light. Beyond the edge of this observable sphere, there may be more universe, perhaps infinitely more, filled with stars and galaxies much like our own. But we cannot see them. Their light has not yet reached us, and if the expansion of space continues to accelerate as current observations suggest, some of that light may never reach us at all, forever chasing a horizon that recedes faster than light can travel. This is a strange and somewhat melancholy thought, that there are regions of reality that we can never observe, never measure, never know, but it is also part of the answer to our ancient question. The darkness between the stars is not emptiness. It is the visible manifestation of a cosmic speed limit, the boundary created by finite time in what may be infinite space. There is another aspect to this resolution that is worth considering as you settle deeper into rest, and that is the fact that many of the stars whose light might eventually fill our sky simply have not been born yet. Stars are not eternal. They form from clouds of gas that collapse under their own gravity. They burn through their nuclear fuel over millions or billions of years, and eventually they die, fading into white dwarfs or exploding as supernovae or collapsing into black holes. The universe is still young, cosmically speaking, and star formation continues throughout the countless galaxies we can observe. New stars are being born at this very moment, igniting their nuclear fires for the first time, beginning to shine light that will travel outward into the cosmos and perhaps, billions of years from now, reach the eyes of observers on some distant world. And even among the stars that have already been born, many are so far away that their light is still in transit, still crossing the vast distances of intergalactic space, not yet arrived at our small blue planet. The night sky you see when you look up is not a complete inventory of all the stars that exist, but rather a snapshot of those whose light has had time to reach us, a selection filtered by distance and time and the finite speed of electromagnetic radiation. What is remarkable, and worth pausing over in these quiet moments before sleep, is that this solution to the darkness of the night sky was intuited, in a somewhat poetic and impressionistic form, long before astronomers had the tools to measure the age of the universe or the speed of light's travel across cosmic distances. In 1848, the American writer Edgar Allan Poe, better known for his tales of mystery and the macabre, published a long prose poem called Eureka, subtitled A Prose Poem, in which he attempted to explain the nature and origin of the universe through a combination of intuition, reasoning, and philosophical speculation. Poe was not a scientist in any formal sense, And Eureka was not received with great enthusiasm by the scientific community of his time, but buried within its sometimes obscure and often flowery prose was an insight that proved to be essentially correct. Poe reasoned that if the universe were truly infinite and filled with stars, the background of the sky would present a uniform luminosity, since there could be absolutely no point in all that background at which would not exist a star. But since this was not what we observed, since the background of the sky was dark, there must be some reason why the light from distant stars had not reached us. Poe suggested that the distance of the invisible background was so immense that no ray from it has yet been able to reach us at all, that the light from the most distant stars was still traveling toward us, not yet arrived, and that this explained the darkness that stretched between the visible points of light. It was a remarkable intuition, expressed in language that was more poetic than mathematical, but it captured the essential truth that would later be confirmed by precise measurement, namely that the finite speed of light combined with the finite age of the universe creates a horizon beyond which we cannot see. More than half a century after Poe's Eureka, in 1901, the eminent British physicist Lord Kelvin, who had contributed so much to the understanding of thermodynamics and the nature of heat, delivered a lecture in which he touched upon a related idea. Kelvin, known for his careful calculations and rigorous approach to physical problems, noted that the stars themselves had finite ages, that they had not been shining forever, and that this placed limits on the amount of light that could have been emitted and traveled through space to reach our eyes. If the stars were not infinitely old, then neither was the total amount of starlight that could possibly exist, and this too contributed to the darkness of the night sky. Kelvin's insight was complementary to the idea of a finite universe, addressing the same paradox from a slightly different angle, and it anticipated some of the reasoning that would eventually become part of the full modern resolution. The stars are not eternal. They are born, they shine for a time, and they die. The light they emit is finite in quantity, bounded by the limited duration of their nuclear burning, and this light must travel at a finite speed across distances that may be immense. All of these factors combine to explain why the night sky, despite the countless stars it contains, remains predominantly dark. And so we return to the image with which we began, the velvet darkness of the night sky, the scattered points of light that have fascinated and puzzled humanity since the first eyes looked upward and wondered. That darkness is not a void, not an emptiness, not a failure of stars to exist in sufficient numbers. It is instead the visible signature of time itself, the cosmic speed limit made manifest in the space between the stars. We see darkness because we are looking at regions from which light has not yet had time to reach us, or at the spaces where light was emitted so long ago that it has already passed us by, or at distances so great that the expansion of space carries the light away faster than it can approach. The darkness is time. The darkness is the finite age of the universe, written across the sky in the absence of light. And in this understanding, the night sky becomes not a mystery to be solved but a testament to the nature of the cosmos, a reminder that we live in a universe with a birthday, a universe that began and has been expanding and evolving ever since. A universe where light travels at a measurable speed and where the most distant regions remain forever hidden beyond the horizon of the observable. As you rest now, let this thought settle over you like a comfortable blanket, the simple and profound truth that explains the darkness above. The universe is 13.8 billion years old, and light travels at 299,792 kilometers per second, and these two facts together create the night sky you see when you look up on a clear evening. The darkness between the stars is not empty. It is full of time, full of light that has not yet arrived, full of stars not yet born, full of the quiet patience of a cosmos that is still unfolding, still revealing itself, still sending its light outward into the void in the hope that someday, somewhere, someone will be looking up to receive it. And so we find ourselves, at the end of this long and winding journey through the history of a question, arriving at the present day, where the darkness of the night sky has revealed itself to be not an absence at all, but rather a kind of presence, a vast and gentle container for mysteries that earlier generations could scarcely have imagined. For when Olbers posed his paradox in 1823, and when Kelvin and Poe offered their partial solutions, they were working with an understanding of the cosmos that, while remarkable for its time, was necessarily incomplete. They knew of stars and planets, of nebulae that might be distant collections of suns, of the mathematics of light and distance. What they could not have known, what no one could have known until the instruments and theories of the 20th and 21st centuries made such knowledge possible, is that the ordinary matter we see and touch and measure, the atoms that make up stars and planets and the neurons in our brains as we contemplate these things, constitutes only a tiny fraction of what the universe actually contains. The numbers, when stated plainly, have about them a quality that borders on the surreal, and yet they emerge from decades of careful observation and mathematical analysis performed by some of the most rigorous minds in the history of science. Of all the matter and energy in the universe, only approximately 5% is the ordinary matter with which we are familiar, the protons and neutrons and electrons that combine to form hydrogen and helium and carbon and iron, and all the other elements listed on the periodic table that perhaps hung on the wall of your classroom when you were young. The remaining 95% of the cosmos is composed of something else entirely, substances or fields or phenomena that we have named but do not yet fully understand, and which remind us that the darkness of the night sky is merely the visible surface of a much deeper darkness, a darkness that permeates the universe at every scale from the spaces between galaxies to the halos surrounding individual stars. The first hints that something unseen might be influencing the behavior of the visible universe came in 1933, from the observations of a Swiss astronomer named Fritz Zwicky, who was working at the California Institute of Technology and who possessed a mind of considerable originality and, it must be said, a personality that his colleagues often found difficult. Zwicky was studying the Coma cluster, a vast collection of galaxies located approximately 320 million light-years from Earth in the direction of the constellation Coma Berenices, and he was attempting to measure the mass of this cluster by observing how quickly the individual galaxies within it were moving. The principle he employed was straightforward and had been used successfully to measure masses throughout the solar system. For the speed at which objects orbit a common center tells us something about the gravitational pull holding them in their orbits, and gravitational pull is determined by mass. What Zwicky found, however, was deeply puzzling, for the galaxies in the Coma cluster were moving far too quickly, their velocities indicating that the cluster contained much more mass than the visible galaxies could account for. Zwicky calculated that the cluster must contain approximately 400 times more mass than the luminous matter suggested, and he proposed that this missing mass must take the form of what he called, in German, Dunkel Materie, which translates simply as dark matter. The idea was received with considerable skepticism by the astronomical community, in part because the measurement techniques of the time introduced significant uncertainties, and in part because Zwicky himself had a reputation for making bold claims that did not always survive scrutiny. And so the concept of dark matter languished for several decades, An interesting curiosity perhaps, but not something that demanded immediate attention or explanation. The visible universe, after all, provided quite enough mysteries to occupy the working lives of astronomers, and the idea that most of the matter in the cosmos might be invisible seemed, to many, an unnecessary complication. It was not until the 1970s that the evidence for dark matter became impossible to ignore, and this transformation in our understanding came largely through the patient and meticulous work of an American astronomer named Vera Rubin, who was working at the Carnegie Institution of Washington. Rubin had faced considerable obstacles throughout her career simply because she was a woman in a field dominated by men, being denied access to certain telescopes and observatories, being discouraged from pursuing graduate study, and being overlooked for recognition that her male colleagues received as a matter of course. And yet she persisted, because the questions she was asking about the universe seemed to her more important than the prejudices of the institutions through which she moved. And her persistence would ultimately reshape our understanding of the cosmos itself. What Rubin was studying was the rotation of spiral galaxies, those beautiful pinwheel-shaped collections of stars that include our own Milky Way. According to the laws of gravity as articulated by Newton and refined by Einstein, the stars and gas clouds in the outer regions of a galaxy should be moving more slowly than those closer to the center, for the gravitational pull decreases with distance from the concentrated mass at the galactic core. This is precisely what we observe in our own solar system, where Mercury, the innermost planet, completes an orbit in just 88 days, while Neptune, distant and cold, requires 165 years to complete a single journey around the Sun. Rubin and her colleague Kent Ford developed instruments capable of measuring the velocities of stars at different distances from the centers of galaxies, and they expected to find these velocities decreasing in the outer regions, tracing a gentle curve downward as the gravitational influence of the visible matter diminished. What they found instead was something altogether different and deeply strange. The rotation curves of the galaxies they studied remained essentially flat, meaning that stars in the outer regions were moving just as quickly as those closer to the center, as if there were additional mass distributed throughout and beyond the visible disk of the galaxy, mass that could not be seen but which exerted gravitational influence nonetheless. Galaxy after galaxy showed the same pattern, the same flat rotation curve that defied explanation unless one accepted that most of the mass in these galaxies was invisible. Rubin's observations, combined with improved measurements of galaxy clusters that confirmed Zwicky's earlier findings, gradually convinced the astronomical community that dark matter was not a curiosity but a fundamental component of the universe, outweighing ordinary matter by a ratio of roughly 5-1. We still do not know what dark matter actually is, and this is one of the great unsolved problems in physics and astronomy today. It does not emit light or absorb it. It does not interact with ordinary matter except through gravity, and it passes through our planet and our bodies at every moment without leaving any trace that our instruments can detect. Experiments' deep underground search for the rare occasions when a dark matter particle might collide with an atomic nucleus, and particle accelerators attempt to create dark matter in the laboratory, but so far these efforts have not yielded a definitive detection. The darkness that surrounds us, then, is not merely the absence of starlight reaching our eyes, but something more profound. A kind of substance that fills the cosmos and shapes the distribution of galaxies and yet remains utterly invisible and largely unknown. And as if the mystery of dark matter were not sufficient to humble our understanding of the universe, the late 20th century brought another discovery that was perhaps even more startling: a revelation about the fate and nature of the cosmos that emerged from careful observations of a particular type of stellar explosion. The story of this discovery begins with two teams of astronomers who were, in the late 1990s, engaged in a project to measure how the expansion of the universe might be slowing down over time. Since the universe began with the Big Bang, the mutual gravitational attraction of all the matter within it should be working to slow this expansion, like a ball thrown upward gradually losing speed as Earth's gravity pulls it back. By measuring how quickly distant objects were receding from us at different points in cosmic history, astronomers hoped to determine the rate of this deceleration and thereby learn something about the ultimate fate of the universe. The tool they used for this measurement was a type of stellar explosion called a Type Ia supernova, which occurs when a white dwarf star in a binary system accumulates enough matter from its companion to exceed a critical mass and undergo a catastrophic thermonuclear detonation. These explosions are useful for cosmological measurements because they all release approximately the same amount of energy, meaning that their apparent brightness as seen from Earth can be used to calculate their distance, much as you might judge the distance of an approaching car at night by the brightness of its headlights. One team, led by Saul Perlmutter and known as the Supernova Cosmology Project, was based primarily at Lawrence Berkeley National Laboratory, while the other, led by Brian Schmidt and Adam Rees and called the High Z Supernova Search Team, operated out of the Mount Stromlo Observatory in Australia and other institutions. Both teams were searching for distant supernovae, measuring their brightness and their redshift, and both teams expected to find that the expansion of the universe was gradually slowing. What they found instead, when they announced their results in 1998 and 1999, was that the expansion of the universe is not slowing down at all, but rather accelerating, the galaxies rushing apart from one another faster and faster as time passes, as if some unknown force were pushing the cosmos apart against the pull of gravity. This was not what anyone had expected, and the implications were so profound that both teams initially suspected their measurements must contain some error, some systematic problem that was producing a spurious result. But as they checked and rechecked their data, and as the two independent teams found themselves converging on the same unexpected conclusion, it became clear that the universe was indeed behaving in a way that no one had anticipated, expanding ever faster into the infinite darkness. The cause of this acceleration has been given the name dark energy, though this name is perhaps more a label for our ignorance than a genuine explanation. Dark energy appears to constitute approximately 68% of the total energy content of the universe, making it by far the dominant component of the cosmos, and yet we understand it even less than we understand dark matter. It may be a property of space itself, a kind of energy inherent to the vacuum, or it may be something else entirely, a new field or force that has not yet been incorporated into our theories of physics. The discovery of dark energy was recognized with the Nobel Prize in Physics in 2011, awarded jointly to Perlmutter, Schmidt, and Rees, an acknowledgement of how profoundly their observations had changed our understanding of the universe in which we live. And so the darkness of the night sky, which once seemed to pose a simple question about the distribution of stars, has revealed itself to be a window onto mysteries that extend far beyond the merely visible. When we look up at the dark spaces between the stars, we are looking at a cosmos that is mostly invisible to us, filled with dark matter we cannot see and driven by dark energy we do not understand, expanding ever faster toward a future that our current theories struggle to predict. The darkness is not empty, not at all, but rather teeming with structure and substance that our eyes and our instruments can only partially detect. This was made dramatically clear in 1995, when astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky in the constellation Ursa Major, a region that appeared utterly black and devoid of interest, and left the telescope's camera collecting light for 10 consecutive days. The patch of sky they chose was tiny, smaller than the apparent size of a grain of sand held at arm's length, and it had been selected precisely because it seemed to contain nothing at all. No bright stars, no known galaxies, no obvious targets for observation. What the accumulated light revealed, however, was astonishing, for this apparently empty darkness contained approximately 3,000 galaxies, each one a vast island universe containing billions of stars, stretching back through time to the earliest epochs of cosmic history. The darkness had been, all along, full of light, full of structure, full of worlds upon worlds that the naked eye could never have suspected. This tradition of deep observation has continued into our own time, most recently with the James Webb Space Telescope, which in 2022 produced its own deep field image, revealing galaxies that emitted their light more than 13 billion years ago, when the universe was less than a billion years old. These distant galaxies appear as faint smudges of light against the darkness, their photons having traveled across the expanding cosmos for most of the history of the universe to reach our instruments, and they tell us that the process of galaxy formation began very early indeed, much earlier than many astronomers had expected. The darkness of the night sky, then, is not a testament to emptiness but rather to distance and to time, to the vastness of the cosmos and to the finite speed at which light travels across it. We have come a very long way from Olbers and his paradox, from the simple observation that the night sky is dark and the puzzle this seemed to pose for an infinite and eternal universe. The darkness, we now understand, arises from the youth of the cosmos, from the finite time that light has had to travel, and from the expansion that stretches and dims the radiation from distant sources. But the darkness also holds, within its apparent emptiness, mysteries that earlier generations could not have imagined, substances and forces that constitute most of the universe and yet remain largely beyond our comprehension. The night sky, when we look up at it now, is not merely dark, but dark upon darkness, a visible surface concealing depths of invisible structure, a question that has been answered only to reveal further questions, stretching outward and backward to the very edge of time itself. And so we arrive at a place of quiet rest, where the darkness that surrounds us on any clear evening becomes not something to be explained away, but something to be gently held in contemplation, a presence as much as an absence, a gift wrapped in the softest black velvet that the universe could weave from its own expansion and its own finite age, and from the simple fact that light, however swift it seems to us, still requires time to cross the unimaginable distances between things. When you look up at the night sky now, perhaps from a garden chair or through a window left open to the cooling air, you are seeing something that generations of thinkers puzzled over for centuries. And the answer, as we have discovered together through these gentle pages, is not that the universe is empty or that stars are few, but rather that the universe is young enough and expanding quickly enough that most of the light that has ever been emitted by most of the stars that have ever existed simply cannot reach us, and perhaps never will. And this limitation, this cosmic boundary drawn by time and distance and the stretching of space itself, gives us the darkness that allows you now to rest your eyes and quiet your thoughts. There are places in the universe where this darkness is more profound than anything we experience from Earth, regions so empty that they challenge even our expanded understanding of what emptiness might mean. And one of these places bears the name of an ancient constellation, the herdsman Boötes, though it lies far beyond any star that you could see with your eyes, far beyond the nearby galaxies, out in the deep field where astronomers point their largest telescopes to count the countless island universes scattered across the cosmos. The Boötes void was discovered in 1981, and when astronomers first mapped its boundaries, they found themselves confronting something unexpected: a roughly spherical region of space stretching across 330 million light-years, a distance so vast that light itself would need 330 million years simply to cross from one side to the other. And within this enormous bubble of space-time they found almost nothing at all. Just 60 galaxies scattered through a volume where statistical models suggested there should be thousands upon thousands, where the normal distribution of cosmic structure would predict a rich tapestry of spiral arms and elliptical halos and irregular smudges of starlight, all the varied forms that galaxies take when they are allowed to form and flourish. 60 galaxies where 2,000 might have been, and between them, nothing but the darkness itself. A darkness so complete that if you could somehow transport yourself to a planet orbiting a star in one of those lonely galaxies, and if you looked up at the night sky from that unimaginably remote location, you would see almost no other galaxies at all, just the stars of your own cosmic island, and then, in every direction, the deep and perfect black of empty space extending further than any telescope could probe, further than any imagination could comfortably travel without feeling something like vertigo at the sheer scale of the absence. How such a void came to be remains something of an open question, though theories suggest that tiny fluctuations in the early universe, variations in density so slight that they can only be measured in parts per 100,000, might have been just slightly less dense in that particular region, allowing matter to flow outward over billions of years, evacuating the space like air slowly leaving a room through cracks too small to see, until what remained was this vast bubble of near-nothingness, a reminder that the universe, for all its billions of galaxies, is still mostly made of the spaces between things, the darkness between the points of light. And yet from our vantage point here on Earth, on any clear and moonless night far from the glow of cities, the sky appears rich with stars, more than we could ever hope to count in a single evening of patient observation. And this is worth pausing to consider as well. This abundance that exists alongside the darkness, this sprinkle of lights that has inspired mythology and navigation and wonder since the first humans looked upward and asked what those distant fires might be. The number that astronomers have settled upon, through careful studies and statistical analysis, is approximately 2,500 stars visible to the unaided human eye on a clear night. Though of course you can only see half the celestial sphere at any one time, and your particular latitude determines which stars pass overhead during which seasons. But in principle, if you could somehow see in all directions at once, you would find about 2,500 points of light bright enough to register on the human retina without assistance, bright enough to have been given names by ancient peoples, bright enough to form the constellations that different cultures drew across the darkness like pictures sketched on black paper. 2,500 stars seems like a generous number when you are lying on your back and letting your eyes adjust to the dark. When the longer you look, the more pinpricks of light seem to emerge from what you first thought was empty space. But consider this figure against the true population of our galaxy alone. The Milky Way, that faint band of pale light that arches across the summer sky and reveals itself, on the darkest nights, as countless stars too dim to see individually but bright enough together to paint a soft glow across the heavens. Within that band, within the spiral arms and central bulge of our own cosmic island, astronomers estimate there are between 200 billion and 400 billion stars. a range so enormous that the uncertainty alone encompasses more stars than there are grains of sand on many beaches. And yet our eyes, remarkable as they are, can perceive only 2,500 of them, a fraction so small that it requires scientific notation to express without running out of zeros. Something like one star in 100 million within reach of human vision on even the clearest night. This is not a failing of our eyes but simply a consequence of distance and brightness, a reminder that we are small creatures on a small world orbiting an average star in one arm of one galaxy among hundreds of billions of galaxies in the observable universe alone. And yet here we are, conscious and curious, able to use mathematics and instruments and patient observation to deduce the existence of all those stars we cannot see, able to understand our own limitations and in understanding them, somehow transcend them. There is a photograph that captures this perspective better than any other. A single image that has become one of the most reproduced and contemplated photographs in human history, taken not from Earth but from a small spacecraft that had spent more than a decade journeying outward through the solar system, past Jupiter with its swirling storms, past Saturn with its icy rings, past the blue-green globes of Uranus and Neptune, and finally, at a distance of approximately 6 billion kilometers from home, turning its camera backward one last time to look at the place from which it came. This was Voyager 1, on the 14th of February in 1990, and the image it captured showed Earth as a single pixel, a tiny point of pale blue light suspended against the vast darkness of space, barely distinguishable from the scattered noise in the image. A fleck of brightness in a beam of sunlight that happened to cross the frame. And when the astronomer Carl Sagan saw this image, he was moved to write about what it meant. About how every human being who had ever lived, every king and peasant, every inventor and destroyer, every moment of love and loss and ordinary afternoon, had taken place on that tiny mote, that pale blue dot suspended in a sunbeam. There were no borders visible in that photograph, no evidence of the names we have given to places, no trace of the stories we tell ourselves about who we are and why we matter, just a single point of light, barely there at all, surrounded by the cosmic dark that Olbers once asked about and that we now understand as the consequence of finite time and expanding space. The darkness that makes our existence possible and that wraps around our small world like the gentlest blanket, asking nothing of us but perhaps a moment of quiet appreciation. And this darkness, this gift of the cosmic night, will not remain as it is forever, for the universe continues to expand, carrying distant galaxies away from us at speeds that increase with distance, and in the very far future, in a time so distant that numbers lose their meaning, perhaps 100 billion years from now, this expansion will have carried every galaxy beyond our observable horizon, stretching the light they emit into wavelengths too long to detect, too red and then too faint and then gone altogether, leaving future astronomers, if there are any, seeing only the stars of the Milky Way against a sky grown truly dark. A universe that appears to contain only a single galaxy surrounded by perfect emptiness, with no evidence remaining of the cosmic community that once existed beyond the local shores. Those future observers would have no way of knowing that other galaxies had ever existed, no lingering light from the cosmic microwave background to tell them about the early universe, no distant supernovae to measure, no gravitational ripples carrying news from beyond the horizon, just their own island of stars and the deep darkness pressing in on every side, a loneliness so complete that they might construct entirely different theories about the nature of reality, never suspecting that they live in a universe once filled with light. And even this isolation would not be the final state. For physics suggests that the universe is proceeding toward what some call heat death. a condition of maximum entropy where all differences in temperature and density have smoothed themselves out over spans of time that make 100 billion years seem like the first few moments after dawn. A state of perfect equilibrium where no useful work can be done because there are no gradients left to exploit. No hot and cold. No high and low. No concentrated energy to disperse. Just a thin mist of particles at nearly absolute zero, drifting through darkness that will never again be broken by starlight. This is sometimes called the final state, though physicists remain appropriately humble about predicting the very long-term future of existence. And there are theories that suggest other possibilities, quantum fluctuations that might seed new universes, or exotic physics we have not yet discovered. But in the most straightforward reading of our current understanding, the cosmos is heading toward a stillness so profound that it makes the Boötes void seem like a crowded marketplace. A silence so complete that the concept of silence itself loses meaning when there is nothing left to be quiet. But that future is so distant that it need not concern us as we rest here in the present moment, on this small planet circling this ordinary star, looking up at a night sky that is neither too bright nor too dark but just right for creatures like us. Creatures who evolved under these particular conditions and who find the darkness restful and the stars beautiful and the whole arrangement somehow fitting for beings who ask questions and occasionally, improbably, find answers. We exist, it seems, in a special window of cosmic time, a brief epoch when the darkness still contains information, when ancient light still travels across space to reach our telescopes and our eyes, when the questions that Olbers asked can still be answered by looking outward and backward into the depths of time, when the universe is old enough to have formed stars and planets and creatures capable of wonder but young enough that we can still see the evidence of how it all began. This is not a privilege we earned but a circumstance we inherited, a cosmic accident of timing that places us at a moment when the night sky is dark enough to see the stars but not so dark that we have lost all connection to the distant past. And there is something peaceful in acknowledging this, something restful in knowing that we are part of a universe that has unfolded according to principles we can understand. That the darkness above us is not mysterious but simply a consequence of finite light traveling through expanding space. That the absence of brightness is itself a kind of answer to a very old question. So as you let your eyes grow heavy and your thoughts grow soft and quiet, consider that the darkness you rest within is the same darkness that Kepler and Olbers and all those careful thinkers wondered about. And that we now understand why it must be dark, and that this understanding does not diminish the beauty but only deepens it. For we are small and the universe is large and the light comes from very far away and has traveled for a very long time to reach us. And somehow, improbably, we are here to receive it. And that is enough. That is more than enough. And you may rest now in the cosmic dark, knowing that it holds you gently and asks nothing in return.